Good morning, everyone. Happy Friday. It really is a pleasure to introduce Dr. Kaixuan Kang, who is one of our UTIG Distinguished Postdoctoral Fellows this year. Dr. Kang holds a PhD in geophysics from the University of Colorado in Boulder, MS in geophysics from the Chinese Earthquake Research Institute, and a bachelor's in geodesy from the University of Wuhan. Prior to her PhD program, she was an assistant and later associate professor at the Chinese Earthquake Research Institute, using gravity and GPS measurements to understand loading related to hydrological variations on Earth's surface. Her research interests include finite element modeling, the viscosity structure of the mantle, glacial isostatic adjustment, and how these processes impact past, present, and future sea level change. In particular, her work has shown that the large stresses induced by deglaciation can lead to order of magnitude changes in mantle viscosity, providing a previously overlooked feedback to ice dynamics. And as a postdoctoral fellow here, she is working with Torsten Becker in collaboration with Jerry Mitrovica at Harvard on better understanding these feedbacks, and in particular, whether rapid ice mass in Antarctica can trigger them and feedback to ice loss. So without further ado, help me in welcoming Dr. Kang.
Thank you, Benjamin, for a very good introduction to me, and also thank you everybody being here. And today I will talk about how I just model the glacial isostatic adjustment by the finite element numerical modeling with the non-Newtonian rheology in the upper mantle included. And I will also introduce my proposed ongoing work in UTIG on how I will imply the non-Newtonian rheology, GRA modeling to learn more about the Antarctic Ice Sheet Evolution. So in today's talk, I will talk about first the background of the general GRA process, and then talk about two projects in my PhD work. One is about how I constrain the deglaciation history by paleo registry level data. And another, the second project is how I simulate the GRA modeling with non-Newtonian rheology included in the upper mantle. And then I will talk about the very exciting part I'm working on, how I investigate on the evolution of the Antarctic Ice Sheet Evolution with the non-Newtonian rheology. Okay, so what is the glacial isostatic adjustment? And when we do the geodynamic modeling, people usually make some assumption on the Earth rheology. So for example, when we deal with mantle convection for those kind of millions of years for this long-term time scale process, we treat Earth as viscous fluid. And on the other hand, when we consider, for example, the signal from seismology or post-seismology, those time scales of about several days to seconds, those kind of very short time scales, people treat the Earth as elastic. But for the GRA, which the time scale is from thousands of years to the decades, for this intermediate time scale, people usually treat the solid Earth as a viscoelastic solid material. This means when we put loads like ice on the Earth, and then we have two different deformational response. One is the elastic deformation; it's instantaneous response to this force. Another is the viscous response. This is time dependence. So this means if the force is gone and the response is still ongoing. So this is how people just very interested in the GRA problem, because signal is gone, but the response from the mantle flow is ongoing. We can observe those signal to learn what happened in the past. And consider all of those ice mass change and the ice melted water going to the ocean, also the mantle flow, all of this system, this surface mass and mantle interior mass reconstribution, all of those mass reconstribution will perturb the gravitational field of the Earth. So we also have a gravitational field response. And the third response is the rotational response, because you can say the GIA is just a global problem. So this global mass redistribution will perturb the moment of inertia of the Earth. So this will perturb the Earth centrifugal potential field again. All of this will feed back to the deformation response. So as I showed here, the GIA is a dynamic interplay among the ice, the ocean, and the solid Earth. It's very complicated, and also for a given loading history, this isostatic response is mainly governed by the density of the Earth. Also, another very important parameter is the rheology of the Earth. Okay, so talk about the rheology of the Earth in the GIA world. So the left one, the left one. So from left to right is from the easier one to the complicated one. So as a very previous study, people usually use a very simple 1D spherical symmetric Earth, like they have the layered viscosity, mantle viscosity to model this GIA process. For example, I showed here, there's two very famous 1D viscosity structure. One is from Departier's group. We call this VM5A. We can say their viscosity structure is 1D, but they have multiple layers, 4 layers and 4 more layers. But the viscosity increase, generally very smooth from upper mantle to lower mantle. And another group, in Lambach's group, they also have the AU ice, and you can see the green curve. They have very large, almost 1 to 2 order of magnitude increase from upper mantle to lower mantle. So this is very contrast viscosity structure. But the surprise is this people use this two viscosity structure and coupled with their own ice model, both they can work to fit some part of the relative sea level data. And so this is 1D viscosity structure. And then if we want to consider more realistic Earth, for example, the temperature, the lateral viscosity changes in the Earth, and then people usually took this 3D viscosity structure in GIA model. They will give us more like the regional or locally GIA simulation for this process. And then another aspect is from the laboratory. From the laboratory experiment, you can see they do the laboratory experiment in the lab situation, but they do the extrapolate from the lab situation to the Earth and the temperature and pressure situation. And then you can see in the Earth mantle, both the diffusion creep or the linear creep, also the dislocation creep or the non-linear creep, both they can occur in the condition of the upper mantle. So this is also, people also use linear or non-linear rheology to do this GIA model. Okay, Earth model, and then we will talk about the ice model. Here I show 3 different ice models at 18,000 years ago. So from Lambach's I6G, from Departier's I6G, from Lambach's NU, and from NAS another model from this group. And you can see roughly the ice margin is almost very similar between those 3 models, but the ice height, you can see they differ a lot, right? They differ a lot. Also, if you compare the time series, the time series of the sea level equivalent ice volume, the sea level equivalent ice volume is just basically if we put the amount of the ice melted water globally constantly in the ocean. So this is just the sea level equivalent ice volume. They differ a lot, right? So you can see present day we know more present day, so it just consistent because they're relative to present day. But if we go back to last glacial maximum, they differ a lot. So this makes us think how they reconstruct those kind of ice height model. Yeah, there are some constraints from geological and glaciological events. For example, here, difficulty A use this ice margin migration. So you can see just the migration with time. Different color means different time. So just the migration, and then the whole ice sheet in North America gone around 8,000 years ago. So this kind of ice margin we can know from geological event, but the ice height above those regions, how can we reconstruct it? We can have some sample or scattered geological events at here or there, but if we want to know the continuously, just not continue, but like continually, spatially continue model, we need to imply the GRA model to do to consider the physical. How the force and how the Earth responds to the force from those ice, because we know this response now, and then we can reconstruct those ice height based on GIA model. But to do this GIA reconstruction, we need a section of the Earth Rheology model. So this will cause a problem for those kind of ice height model, because all of those ice height model reconstructed by GIA model, they coupled with certain Earth model. Those group just made some assumption on those. They're not independent ice height model. Okay, we have for GIA, the force include two parts. The one is ice, the ice history. Another is we need to consider about how those ice melted water distributes to the ocean. So this will give us the ocean loads, how those ocean loads change, and how Earth responds to this kind of global ocean load change. So to the first order signal, we can just distribute all of those amount of ice melted water into the ocean globally as a constant. This is just the first order. But if we want to consider gravitational self-consistent ocean, so we need to include more than this the first constant, global constant component. For example, I showed here, this is from Lin's work. For example, those show the ice melt, amount of ice melt, and then this is the elastic response if those ice melted into water, and how those sea level change globally. You can say it distributed into the ocean. It's not as constant. It has spatial pattern, right? So close to the previous ice, there's ice sea level fall, and then if we go further to the far field, and then there's sea level rise. Okay, this is the gravitational of the ocean, and also we need to consider the geometry of the ocean. So if we can say those ice mark, the ocean shoreline migration in the near field, also in the far field, they have different pattern. For example, in the near field, if the ice is melted, and then due to the land underneath those ice will uplift, and then also the ice melted water goes into the ocean, and in near field, the shoreline will just go this way. It looks like all flat, but in the far field, it's the opposite happen. So how we model all of those complicated ocean loads for the ocean parts of the forces for GIA model? Yeah, we solve the sea level equation for the gravitational self-consistent ocean. So this this theory is very classic from Barry Clark, and then improved by Glenn, Mitchell Vega, and Cano. So they just have a very robust foundation for the GIA theory. So the equation, for the equation here, the left is the ocean loads. We can call this ocean loads out of the sea level. It's the same in the ocean, right? It's different in the land, but it's the same in the ocean. So this is our loads. Also, this is also one of our results from the GIA response to the sea level. So let's consider the first order signal. This is what I mentioned. We call this eustatic sea level. So this basically those kind of amount of ice melted, and then we change those ice into the height, ocean height change. This is global constant. This is globally constant. So we put water just globally, globally everywhere. And then we need to use the GIA response to do the second order correction, like I showed here. So like I showed here in left. So this is like the sea level is the sea level is bounded by two surfaces. One is the ocean surface, the blue curve, and another is the solid earth surface, or the asymmetry, or the topography, we can call them. So these two surfaces, if the ice melted, this is the ice. If the ice melted, this will perturb both of these surfaces. So if go to bottom, we can say if we have perturbation to the top surface, we have perturbation to the bottom surface, and then we can know how those perturbations can cause the sea level change. Basically, the geoid, because the surface, the ocean surface follow the geoid potential surface, right? So the geoid minus the uplift of the bedrock on the ocean bottom. So, and then we will have the GIA solver to solve this part. For the gravitational self-consistent ocean, we will also consider the shoreline migration. This is what I just talked about for the geometry of the ocean change, right? So we include all of those. Effects in our sea level equation, and then we can calculate back the sea level change. The tricky thing is, yes, we have those GIA perturb sea level change, and then this sea level change is one of the input of my GIA model. So they will just go further to perturb second time. So we need a solution here to solve this problem. Okay, so we have our frozen part, our ice load, our ocean loads. We have our Earth rheology, our Earth model. So, okay, so we have all of those ingredients for GIA, and how do we simulate the geodynamic system with loads? So this is the physical law we used in our model. So basically, this is governing equations include the mass conservation, the momentum conservation, and the Poisson's equation give us the gravitational perturbation. And then we consider boundary conditions, and all of those forces I mentioned about the ice and the ocean will go into this boundary conditions. Also, this mechanic we use Maxwell Maxwell solid mechanical properties include both elastic and viscous properties here. We use sitcom SVE, which is a finite element modeling package, and then we can use 3D spherical Earth model to do this, to consider more realistic Earth. Okay, this is all the GI model components I mentioned. You can see we have the input ice and the load ocean. Old loads ice will come from the ice, the ice history, and then we can have the sea level equations to include the ocean loading, and then we will make some assumptions or some constraints for the Earth structure and rheology, and then we do the GI model to solve the governing equations, and then we will have the outputs. They have multiple different outputs. In my study, I usually I mainly consider the relative sea level change, also the vertical solid Earth deformation. We will also have other response. And then, this is the model parts. And then we will have some data from paleo sea level data on the present day, gravity satellite data, also the vertical, horizontal land motion from GPS. We have all of those observations, and then we can use those observations to learn more about our model to do this, to improve our model and to learn more about the physical things. And more recent, I think this is pretty new. People realized that this GIA solid Earth deformation will coupled with the ice sheet dynamic model. So they will just do this part will also affect those ice loads. So this is just the GIA and ice sheet dynamic modeling coupled with each other. Okay, now I will talk about my first project, how I use the paleoretic sea level changes to constrain the ice melting history. So there's a very famous problem here. So I mentioned this missing ice problem. So what this problem means? So we can say there should be a balance. I mean the mass conservation between the ice and the ice melted water. So this means if we sum up all of those ice volume here in the north hemisphere and south hemisphere. So if we sum up all of those ice, the melted, and then relative to present day, if those melted ice water goes into the ocean, this kind of sea level equivalent ice volume should agree with the far-field relative sea level data signal. So this is data we observed from the field work. So these two should agree, should balance with each other because the mass conservation. But people just fight from the paleo relative sea level data, those observations. For example, Lambeck showed here the post last glacial maximum sea level rise is around 132 meters. So this is from data, but look back to our ice height model here. But if we consider the expansion of the oceans, also the mountain glaciers, the groundwater, consider all of those effects. If we add that, if we sum up all of those ice volume at last glacial maximum, we only got 140 meters. So there is a deficit in ice volume. We don't know where we need to put those ice on right now. So this means this discrepancy between the model and the data in the last glacial maximum volume could result from some unknown sources of the GIA modeling. It could come from maybe we we need to modify the ice melting. Maybe we need to modify the ice model people usually use now, or maybe we need to include more physical in the GIA model. Also, so talk about more about those uncertainties in ice model. I just simply compare the NU ice and ISG ice. I showed here, you can see this is last glacial maximum spatial distribution of these two ice model, and this is the difference between these two ice model. So they differ a lot, right? So the ice height around here and Fennoscandia, also the Antarctica, they just differ. I didn't give a scale here, but they differ. At some size they differ around 1,000 meters. And if we compare the time changes with time, the global ice volume, the NU model, basically they include more ice than ISG. Also, the Antarctica ice NU model include like the NU ice in Antarctica is much thicker than ISG ice. As I mentioned before, all of these two ice models, they differ a lot here and there, but both of these ice models, they can fit some part of this relative sea level data. So I gave a map here. We collected from different groups globally of those paleo sea level data. For example, from Lambeck's around here and from Deep Ice, Vetches, and Ingelhart. Let's go through those. You can see the spatial distribution of this data is very uneven. There's lots of data around Hudson Bay because there's no ice here, so they left many geological evidence. We can figure out how those relative sea level have migrates here. But also the same. We should have more data here, but I only collected limited data around Fennoscandia. But in Greenland and Antarctica, we can imagine nowadays they're still covered by ice. So you can imagine the relative sea level data will be very limited there, here and there. So they will give us more challenge to constrain those ice model in Greenland and Antarctica. Also the far field, we call this far field relative sea level data, which is far away from the ice sheet. So basically in this open ocean, those relative sea level data will give us is more sensitive to the total volume of the ice. They cannot tell those sea level rise come from here or there, but they can tell us the total ice volume. Total ice volume constraint. I showed two examples of the relative sea level data sets. One from Vetches. You can see those data around Hudson Bay. The physical pattern is the relative sea level fall around those regions mainly caused by the land uplift. Also show another group of the data set from Ingelhart. This is from the east coast of North America. You can see the pattern, it will be different. They just have a sea level rise, right? Sea level rise here. So sea level pattern is different globally. So they show different pattern around the near field, also semi-far field, also the far field. So this is the data constraints to our model. And then we have the data, also we have the ice model, and then we can use this to input and output to test like the GIA, the Earth Rheology as a black box. We just twist. For example, here I use a two-layered we have lithosphere here, but as constant. And we verify the upper mantle viscosity and lower mantle viscosity to adjust these two parameters to see, okay, which grade will best fit to one particular relative sea level data given by one particular ice model. Example here, the first column I show here is both the NU ice and the ICG ice, how this grid search method, we call this the viscous misfit map, can give us which pair of the upper and the lower mantle viscosity will give us best fit to the relative sea level data in North American region. Also, this is for Venus-Gadian. And then this is how those two ice models can fit to far field with a particular pair of the upper mantle and lower mantle viscosities. The conclusion is the North American relative sea level data can give us compare this three different sea level data sets. The North American relative sea level data can give us a better constraint because you can see the region is very low, very small. But if the Venus-Gadian relative sea level data, the lower misfit region is very broad. So it's not as much as good as North American relative sea level data. And we found some problem for the ICG far field relative sea level data and model fit misfit here. I will talk about later about this problem. Okay, this is the problem we found. So if we have our preferred Earth model, and then we will go back to say, okay, we have this overall good Earth model can fit those relative sea level data, but there are still some region that the ice model cannot work pretty well. For example, the ICG, they cannot fit pretty well in this region. Also, the ICG, to fit the far field, they have a shift here. It looks like there is not enough ice melted into the water in ICG to fit the far field relative sea level data. And then we go back to, we want to just modify those ICG based on those misfit map. We construct three kind of different modified ice model. All of those ice model, we just try to increase the ice height either in Antarctica or in North American region. And we compare those modified ice with the original ICG ice. And we find if we include more ice, either in North America region or in Antarctica, they can improve the misfit to the far field relative sea level pretty largely. You can see the black one is the original misfit for the far field, and then if we include those ice in ICG, all of those misfit will improve pretty well. And then this is the relative sea level. We compare with we modified the ice model, and then we compare with with some relative sea level data. And then I just want to point out, the near field, some modification don't work, but overall, if we modify slightly, they can still fit to the data in the near field. Also for the far field, for example, here at this site, our modified ice model can fit the far field pretty well than those solid line, which is already from original one. Okay, some conclusions for my first project. So we can say there are much uncertainties in these two widely used deglaciation history models, and we try to modify those ice model to fit both the near field and far field relative sea level data. Okay, so this is one of the uncertain of the GIA model, the ice models. And another project, another problem is the Earth rheology. Maybe there are also some uncertainties here. So my next project, I just explore the non-Newtonian rheology in the GIA modeling. So non-Newtonian rheology is not new. So you can see they apply all of those. So from microscope experiments in the laboratory, rock deformation, they show this kind of non-Newtonian rheology. Also the post-seismic deformation and geodynamic modeling, they all explore those non-Newtonian rheology. And for GIA, this is also not new. So you can say, people in different group, they use power law or composite rheology in GIA to explore this nonlinear effects. But we found all of those GIA with nonlinear rheology, they try to include those nonlinear effects to try to get a better fit to the data. But in my work, with my advisor, we just want to go back further a little bit and to see some basic physical questions. For example, if we consider the non-Newtonian rheology, we need to deal with the stress, right? Because the viscosity now is stress dependent. So how does the ice-induced mantle stress evolve in space and time? This is a question we want to answer. Another is how those stress-dependent rheology will be affected by the will affect the viscosity variations and how those variations can affect the lattice level change. So this is the composite rheology we used in our model. This equation is come from the microscope laboratory experiment. You can see the mantle rheology is very complicated. It depends on some microscope parameters like grain size, the water content, also the activation energy and and volume, and also depend on the temperature, the pressure, and the stress. And for the composite rheology, we just assume that both diffusion and dislocation creep can both occur in the mantle, and we just combine these two and consider the effective viscosity in this formula. Now you can see the effective viscosity will have a prefactor here. This prefactor will be a combination of all of those different other parameters here. So we just include all of those other effects into our prefactor. And then we will only consider the stress-dependent viscosity. So now the ice-induced stress is spatial dependent, also time dependent. This will cause our effective viscosity now is not only spatial dependent, also will change with time. And another two important parameters here is didn't work. Okay, I cannot go down, so sorry. Okay, one is the transition stress, and another is the background stress here. The transition stress. The transition stress will come from this laboratory experiment, and we choose 3 different transition stress. Like in case 1, I choose the 0.2, megapascal, and this will give us the strongest non-Newtonian rheology. Also, we will consider the background stress. This is a counteract to our non-Newtonian rheology. We will use the average of the global upper-mantle viscous stress from the mantle flow model. Okay, this is, let's try. No. Okay, this is the okay, so this is the average upper-mantle stress evolution. We can say during the glaciation period, because we assume the ice build up linearly, so they will give us a constant strain rate. So we can say the stress and viscosity pattern is almost the same with the ice linearly build up history. But if we go to the right panel, the ice history deglaciation history, we can see the stress increase dramatically during the around 14,000 years ago. This is a fast ice melted water event occurred. So this increased stress will induce weakening in viscosity, which will lead to around 1 to 2 order of magnitude weakening in viscosity. This is a very fast relaxation phase. And then when the ice melting process is done, and then the stress start to go back to its background stress. And then this is a slow relaxation phase. And here we give our stress evolutions on a global scale. And we can see the lithosphere with the ice buildup. The stress in the lithosphere will increase with time because we treat the lithosphere as elastic solid. And then in the upper mantle or lower mantle, the peak of the stress is not at last glacial maximum, but around the 14,000 years ago. This is a rapid ice melted water event occurring here. So you can see the pattern globally. Also, for the time evolution of the regional average stress and viscosity, we can see the similar conclusions from the spatial pattern. We have a very stable stress and viscosity pattern during the glaciation. Also, we have a fast relaxation and followed by a slow relaxation phase during the deglaciation period. So this is the non-Newtonian effects of the uplift and the geoid. Yeah, I want to point out, so for example, around the Hudson Bay here, there is a more rapid uplift occurred here when the ice melted rapidly. And then when the ice melt process is done and followed by a more gradual uplift. And also for the relative sea level predictions, we can see the non-Newtonian rheology has fundamentally important effect on this relative sea level predictions. For example, here for the near field in Norway, one side of the Norway, start from the 14,000 years ago, the Newtonian and the non-Newtonian predictions start to differ from each other. And the largest difference can reach to 30 meters around 8,000 years ago. And then we can see the non-Newtonian rheology relative sea level predictions, they have a more rapid sea level fall and followed by a more gradual sea level fall. We call this like a quasi-L shape in sea level fall caused by this non-Newtonian rheology. And we try to find this feature from the real data. So we just pick up some of this data. We can see they indeed have a very rapid sea level fall at some of those sites, which the shape, I mean the slope is more similar to the non-Newtonian rheology predictions. They have some offset between the model and non-Newtonian. This may cost some other, maybe they caused by the ice model I used. The ice model I used is ISOG, which is coupled with a linear rheology. So if we use this ice model to calculate non-linear effects, they will not just be not self-consistent. So maybe some of that showed here. Okay, so the conclusions from this project is this rapid deglaciation event, for example, around 14,000 years. This is not 14. Around this rapid ice melt water event, meltwater pulse 1A, we can say they will induce large stress in the upper mantle, and then they will lead to a reduction in the mantle effective viscosity of more than 1 order of magnitude. And this weakening in the viscosity should manifest in relative sea level data, also uplift like quasi-L shape. In my study, I only see one of those the most rapid ice melted event here. So now I think about, so how about there are more like similar ice melted or rapid ice melted event in our history. So how about those peaks, and how about those in the future? So now come into this this work I'm working on now. So investigate the Antarctic ice model. So here I show some data people collected for Antarctica. This is from White House paper, and he collect those relative sea level data from West and East Antarctica and do the model to fit those data. And we can roughly say this for the East Antarctica. Their model, the fitness is not bad, right? So they have some of misfit, but not bad. But if we can say the West Antarctica, you can see the model data misfit is larger. This is because in their model, so go back to around 10 years ago, their model, they still use the very high viscosity in the Antarctica. So right now we know in this region, the viscosity of the upper mantle is very low, to 1 to 2 order of magnitude lower than the viscosity they used. Also, the GPS data we have now, I talked about this. So from Bolanos studies, they show those data, the observed GPS uplift rate, the vertical, also the horizontal motion of the present rate. You can see the elastic GRA model predictions are much lower than the data they observed. People use those to constrain the Earth viscosity in the West Antarctica. People just find, okay, in this region, the viscosity is much lower than the normal viscosity used in GRA model. Also, go back to the Antarctic ice sheet and last glacial maximum. Lambert pointed out the ice sheet at last glacial maximum remain very poorly known. So many published estimates, they differ a lot. For example, from Lambert's calculations, the Antarctica contribution to the global mean sea level around 20 to 30 meters at last glacial maximum. They coupled with their assumption of the Earth model. They used 2D upper mantle, lower mantle viscosity with a larger constraint between upper and lower mantle viscosity. Also, DPA, their group, their model, they estimate the Antarctica contribution to the global mean sea level around 30 to 40 meters at last glacial, 40 meters. their Earth model is also very different from other group. And this is White House. They coupled with the geological constraints and the geological models to predict the Antarctica contribution is around 10 to 11 meters. So all of those, you can see all of those studies, they differ a lot. The range is from 8 meters to 30 meters, right? For only Antarctica part. And all of those studies, they do not include strays from local relative sea level data in Antarctica that are older than 8,000 years ago, because the data we collected they can only go back to 8,000 years ago. We know nothing about the previous ice sheet evolution in Antarctica older than 8,000 years ago. This will make us to think about, what missing here? Maybe some basic physical parts we didn't include in the GIA model to estimate the Antarctic ice sheet at last glacial maximum. Or maybe we need to modify the ice sheet model to deal with this huge agreement between different studies. So my work here, I have my proposed work include 2 steps. I'm just working on the first step, just the very start point. I want to try to adopt the non-Newtonian model in those kind of similar studies to explore the impact or the effects of the Antarctic ice sheet volume from last glacial maximum to present day, and how they can affect the sea level changes. And after this, I also want to do furthermore to perform the first coupled sea level and ice sheet modeling with the non-Newtonian rheology to see if they can affect the past and future Antarctica ice sheet evolution. Okay, so I think this is all I have for today. Thank you so much.
Awesome. Thank you so much. Questions for Kaixuan? We have one up in the front, Luke.
Yeah. Yes. When you look at your rheology, the non-Newtonian rheology, what you call the transitional stress, is that going from dislocation creep to diffusion creep?
Yeah, the transition stress the definition is the dislocation creep and the diffusion creep. They contribute equally to the total strain rate. So it just like a threshold between the linear and the non-linear. So if the ice-induced stress is very low, and then they will not surpass this threshold, and then the deformation would be linear. But if the ice-induced stress increase, for example, due to the rapid ice melting event on the surface, and then the stress in the upper mantle would just increase dramatically, as I showed in the map. So, and then this ice-induced stress will surpass this threshold, this transition stress, and then the non-Newtonian rheology will just start to show.
It depends a lot on the water content.
Yeah.
How do you
right.
choose? How do you choose that? It's
very complicated. So another group in Europe to do the non-Newtonian GIA model, they use those kind of microscope parameters from laboratory to do this. They didn't use the transition stress, like this very geophysical conception, right? Transition stress, they use the water contact of the olivine. They use the grain sites. So they all use the microscope laboratory results to do this. But what we're thinking about this is the GIA process is a global one. I think we can only give a constraint on whether this non-Newtonian rheology effect or not. We cannot just constrain those details about those microscope, like grain size or water contact. So my transition stress here, they depends on those microscope parameters. So you can see this transition stress is grain size dependent, also dependent other things, but we didn't go further to say those.
Thank you. What? Yeah.
Thanks, that was a really great talk. So I'm thinking about how you showed you had a lag between the data from Norway and your curve with the ice model in that L-shaped plot. There was like a lag time. And so
I showed one of them. No.
yeah, this one. So I was wondering, like, if you're trying to fit that, how much could you fit by just increasing the starting ice, and how much could be like a real lag in the timing, and how much could be, I don't know, some kind of uncertainty in the viscosity? And so what do you think is the most important thing if you're trying to make that, you know, that the model fit the data?
Yeah, good question. So yes, so if you say this data and the model, so we can show this this feature. So this rapid, the large slope of the feature caused by non-Newtonian rheology. But if we want to consider how our non-Newtonian rheology can fit those data, I think yes, there's two possibilities. Yeah, some people just argue maybe this larger slope of this relative sea level data only caused by the local ice melting history, because ice just melted like this way. And another is maybe, yeah, the non-Newtonian rheology, they have time-dependent viscosity. Time-dependent viscosity, so they can change those shape. They can change those curves. So yeah, it's hard to say how much of the ice model contributes to the uncertainty, or how much of the Earth rheology contributes to this misfit. But based on those the previous research, people usually consider the shape of the relative sea level curve. They're more sensitive to the Earth rheology structure, but the amplitude, I mean those amplitude of those relative sea level, relative sea level data, more sensitive to the ice sheet, I mean the ice height change. So this is why we make the conclusion that our shape, you can say the relative sea level data, the shape is very similar to our non-Newtonian predictions. This is more sensitive to the rheology thing, but we have a offset. So this is kind of the amplitude of this two amplitude difference may be caused by the ice model.
Yeah, thanks.
Hello, thank you very much. It was a great talk. I just have a maybe slightly dumb question, but you were talking about the near field versus far field observations. What is your threshold for near field versus far field?
Yeah, that's just people just use this near field, far field to do this constraint, because this is basically caused by the GRA response. So the GRA response in the near field and far field, they're totally different. You can see the sea level change in near field, sea level fall, and the near far field sea level rise. So the sea level feature is pretty different between the near field and far field. We can figure out by the sea level curves, sea level curves to tell near field or far field.
There's no hard like cutoff of X degrees away from something.
We don't have a threshold. For example, 1,000 kilometers near the ice, we call this near field, or beyond this, we call this far field. We didn't do that, but we just say those different curves, they show different patterns. They can tell us, also this is this is the near field GIA process. That is not process, near field GIA response, and that is far field GIA response.
Thank you very much.
Thank you for your talk. I'm very curious about some of this future work, and in terms of like adapting a coupled sea level and GIA model. And I'm curious about what you think this work implies for the future evolution of the Antarctic ice sheet. Maybe like what do you imagine like future like stress fields looking like, and what should we consider for like the projections and modeling that we do within our glaciology community?
Yeah, thank you for asking. I prepared one slide, but I think the time is not enough, so I didn't show. So yes, so this is my thought about the ice sheet and GIA interaction. So you can see for the time scale, so this is all of those factors can affect the ice stream or the ice sheet flow dynamic modeling. So I just found the glaciation isostatic adjustment. The time scale this is around thousands of years to decades, right? Depends on viscosity, mantle viscosity. In Antarctica, the mantle viscosity is much lower than the other regions. So the Maxwell time scale is around tens of years to decades to thousands of years. So this is can affect our future sea level predictions. So maybe for the decades, for decades to hundreds of years. So this is time scale. And another thought is, you can see from Nobel's paper here. So this is the ice sheet. Yeah, this is ice sheet dynamic. They consider this grounding. They consider this grounding line. Consider this bedrock, or the bedrock elevation. We call this topography. Changes. All of those will change, can be changed by GIA or going ice melting event, also the previous ice melting history. So all of those can affect the boundary of the ice sheet modeling. So this is from the underneath of the ice sheet, and also they will change the ice. The ice melting water go to the ocean, and then the ocean will also change. The sea level will also change around the ice sheet. So if we consider the Antarctica, then there is a marine-based the marine-based portion of this, and GIA model, our output will predict the sea level change around those marine-based ice, this portion. So I think this is also will change the boundary condition of the ice sheet dynamic model, right? So this is how this ice sheet and glacial GIA interaction comes from. I think yes, our outputs will be the boundaries or the inputs to your ice sheet dynamic model, and otherwise your ice sheet height, this model will go into our inputs as my inputs to as a forcing to just drive my GIA model. So this is couple like iteration thing. So we will consider this later.
Lots of exciting work to do actually here at UTIG. I know I have more questions, but in the interest of time, we'll wrap up now. We're lucky that Kaixuan is here with us for a year, so do get in contact with her. I think her office is in the pod where Torsten's pod, Alice, so reach out, students. I think Ethan is taking people to lunch at noon, meet in the lobby, and otherwise let's thank Dr. Kang one more time for a great talk.
Yes.